Antoine Lavoisier's conservation of mass. Now, on the outside, this isn't I mean, it's pretty groundbreaking, like it's a big deal, but it's not the most interesting thing anyone's ever really sat down and looked at. Like, so if we go back to what his reaction was, he took mercury 2 oxide, which was a red solid. He put it in here, this little bulb thing, and he just started heating it. As he heated that little red solid, good morning. What fictional universe would you like to live in? Or do you think it could be fun to live in? Candyland. Ikpreet, good morning. What fictional universe do you think it would be fun to live in? You don't know. Okay. So as he heated his mercury 2 oxide, because mercury metal itself has a pretty low melting point, gentlemen, over there, the mercury and the oxygen in HGO started to separate. If the silvery colored mercury formed and colorless oxygen gas was created. And so you might ask yourself, well, how could he possibly know? Well, when you heat gases, what do? They do what? Oh, when you heat liquids, they steam. But if you're going to heat something, if the oxygen's coming off it, you're not necessarily going to see it. But what does a hot gas do? Sorry? No. Sorry? It flows up. Hot gases rise. And so what this gas would do, it would just it would expand in the space that it's in and follow the path provided by the glass tubing. Putting it in a water bath like this cools that gas down, helps it condense, and it would collect in this glass bulb here. This contraption allowed him to trap the mercury on one side. Mercury, so in this case, the pure mercury over here, and the oxygen gas over here. And then because he's got the oxygen in one spot, the mercury in the other spot, and nothing else in this apparatus, he could measure what was over here. He could weigh it. He could weigh what was over here separately, and then add those masses together. So he's measuring individual masses. And this reaction, he performed hundreds of times. After performing this reaction hundreds of times, because you need to actually verify that you're getting consistent results, he found that as he was doing this, the mass of the HGO was the same as the total mass of all of the mercury and all of the O2, oxygen gas, produced every time. And so this observation was summarized, he summarized it as the law of conservation of mass. And conservation laws in science are a big deal. When something is conserved, that means it's not created or destroyed. It just gets moved from one place to another. It doesn't go anywhere. It doesn't disappear, and that's a big deal. And so he summarized it like this. Mass or matter cannot be created or destroyed. In a chemical reaction. Whether you've got an explosion or whether you've got two liquids that you've mixed that have produced something new, whether you're burning something, the matter that's there isn't being created. It is not being destroyed in a chemical reaction. It's just being moved around. And so this might not seem terribly earth-shattering, but at the time it was. It was a really, really big deal. Because this means now that you can start, if things aren't being created or destroyed, that means you can start to try and find ways to, if you want to isolate a particular compound, if you want to collect a particular kind of element, you can start to pull it out of other compounds, or you can mix two elements together to create a new compound without losing anything. And that was at the beginnings of real chemistry, which in the 1700s, I think the date I gave you was the late 1700s. That really was the birth of what we know today as chemistry. Before then, it was something perhaps you've read about in fiction called alchemy. Which one are we looking for? Yes. This one? Okay. And so what we're going to do is we're going to go to the lab, and we're going to do two relatively simple reactions. We're going to pull out, we're going to mix two things together in an open system, and you're going to see what happens. And we're going to mix two things together in a closed system, and we're going to see what happens there. I'll talk you guys through it a little bit before we go. You'll be doing this in twos or threes, ideally not alone. We don't have very many scales. For energy is also the same. Energy is not created or destroyed, it's transformed. It's the same. And so if energy is not being created or destroyed, and mass isn't being created or destroyed, and you can actually make conversions between the two, which is a weird idea. But foundational, like you probably, I'm assuming, the equation E is mc squared. That is the equation that relates to the conversion of energy. E equals mc squared, stands for energy. Mass, M is mass, and C happens to be a value related to the speed of light. And so if you take, so that equation relates the energy that's available that you can take out of a particular mass or that you can put into magnets. Okay, so here's what you guys are going to be doing today in the lab. There are two procedures. If we don't finish today, we can finish tomorrow. Here's what we're going to do. Part one, you guys are going to mix some sodium hydroxide, which is effectively a bleach ingredient, so you don't want this stuff on your clothes. So you don't need to wear a lab coat. You just need to be conscious of what this stuff is. It will stain your clothes. It will discolor them. It's dilute. It's not very strong. It's 0.1 molar, so it's pretty weak, but it's still something you don't want to get on your clothes. And a dilute iron nitrate solution, which I will provide for you guys. In part one, make sure you read part one really quite closely. You're going to put one of those liquids into a test tube. You're going to put the other liquid at the bottom of a flask. Remember, the flasks are these ones. They're the ones that look like this. That's a horrible drawing. Something looks like that. And you're going to put the test tube inside your flask. Don't tip them until it tells you to tip them. You're going to put one inside the other, and you're going to put a stopper in this thing. And then you're going to weigh it. Don't let these things mix. You're measuring the mass of the flask and its contents. You're going to record your observations. This stapled thing together is where you're going to record all of your observations. And then you're going to tip the flask. You're going to allow them to mix.
Please excuse the disruption. At this time, we are going to shelter in place. All staff and students shelter in place. Activate shelter in place immediately. Activate shelter in place now.
Seriously?
I guess it's class nap time. What a coincidence. We never actually got our class nap.
Probably did this, you bigness. Okay, I'm going to keep talking about because if this ends, it's only 8:30, 25. We have time, we will go to the lab today. And we're going to, what we don't finish today, we will do tomorrow. So I've already got lab equipment booked for tomorrow. So that's part one. Relatively straightforward. You'll make something cool looking. In part two, you guys are going to mix two other things together. It's not, it says here that you're going to use an Alka-Seltzer tablet. You're not going to use an Alka-Seltzer tablet. I didn't find any Alka-Seltzer tablets. You're going to use one of these instead. It's denture cleaner tablets because it does basically the exact same thing. When you put them in water, they will fizz. That's what we want them to do. And they're minty as opposed to whatever Alka-Seltzer. So the orange does smell like mint. We're going to put some water in a beaker this time. That's the flask. This one's the beaker. Nothing weird looking about the beaker. This system is going to represent what? That we talked about over the last flow system. This one's going to be open system. And so, hands up if you've ever played with Alka-Seltzer before. We have not? Okay. None of you? Okay, and you take an Alka-Seltzer tablet, you put it in water. You don't know what's you'll see that. Right? And something. Kind of, yes. It will dissolve, but something else will happen. What you're going to do before you put the denture cleaner tablet into the water is you're going to weigh them together separately. You're going to put your beaker on the scale and the Alka-Seltzer tablet on the scale together. Without mixing without putting one into the other. After you've recorded that mass, you're going to leave the beaker of water on the balance. You're going to take the tablet, you're going to put it into the thing, into the beaker, and you're going to observe. You'll need a stopwatch for this because every 30 seconds you need to record the mass again on this chart here, and then write down any observations for what you will see happening. The scales that you will use are the same ones that we used for the lab equipment lab that we did 2 weeks ago. They're the little silver ones. The problem with those is because they're battery powered, not plugged in, they will shut themselves off after a particular length of time. And so every so often what you need to make sure you do is as you've got your scale poorly drawn in. Your screen. Every so often, what you're going to have to do is you don't want this thing to shut itself off. If it shuts itself off and then you turn it back on, it's going to read what right there? Sorry? Yeah, it's going to zero itself. And you're going to lose all the data that you have. So every so often, I would say every probably 20, 25 seconds, push on the scale. As long as you continue to push on the scale. Because the reaction is going to happen in here, and because it's an open system, what do you expect is going to happen? Sorry? I hope it doesn't overflow. In a closed system, matter is not allowed to leak. So in the closed system, the mass is probably going to stay the same. And you're just verifying that this is going to be true. In an open system, matter is allowed to leak. So theoretically speaking, because this is an open beaker, something may leave. So what should be happening to the mass as we go? Theoretically, it should be decreasing. And so what you're going to do is every so often, you just need to push on the scale with your finger. A large change in mass will keep the scale active. As it is on its own, the small changes in mass aren't enough to keep the thing alive. So every so often, every 30 seconds or so, maybe even less, we'll figure out how long it takes. Push on the scale to keep the thing active. You'll do that you'll watch it for 10 minutes. Recording observations every 30 seconds. And then once you've cleaned up, you're going to make a graph of your data for part 2. And then you've got some questions that you're going to answer as well. Assuming the shelter in place ends, that's what we're going to go do. As long as the shelter remains in place, probably should have closed my blinds. It's not a lot. Okay. While we wait. I want you to flip ahead to this page. While we wait, flip to this page. Okay, so let's pretend we've done the lab. Antoine Lavoisier's results were a big deal. What they allowed us to do, because nothing is created or destroyed in a chemical reaction, things are just moved around. It allowed chemists to start to organize those ideas into what we now call chemical equations. So, a chemical equation is something you're familiar with already. You've seen these things before, almost certainly. We're just going to formalize some of this language. A chemical equation is a statement that uses words or symbols to describe a chemical reaction. It describes the chemicals that you start with, also called the blank, and those that are produced after the reaction has taken place, also called the blank. Words for these things. It's on the page already. When you mix two things together and something new is produced, if something is produced, we call it when you make something. It's a P word. It's on the page. It's a product. If you put a bunch of small pieces together, you have produced a product. You've made something new. So the products are what you get after the reaction has taken place, and the things that you poured into it that you want to react, you call the reactants. So reactants go in, products come out. And when you are making your chemical equations, the reactants generally go on the left, the products go on the right. An arrow indicates the direction that the reaction is happening in. So the arrow always points from reactant to product. So what is reacting? Switch to pink. And what is being produced? So here's an example of a chemical equation. Very simple one. You've got reactant A plus reactant B. This plus sign just means reacts with. So reactant A reacts with reactant B. That arrow means to produce or to yield. Product C and product D. It might only make one product. It might make 3 or 4 products. Whatever is produced gets listed here on the right. Whatever went into what you're making goes there on the left. And sometimes you'll have objects that show up on both sides that didn't actually react, but that they needed to be present. Sometimes in reactions like this, you'll actually see this. I don't know if you've seen this in the reading that you've done, but that symbol in the middle won't have an arrow one way. Sometimes it'll have an arrow both ways. Hands up if you've ever seen one of these in any sciencey reading you've ever done. Malik, is that a hand yes? Or is that, you have? Okay. So what an arrow both ways means is that whatever is written here can slide back and forth. Like if you mixed A and B together, it might produce C and D, but when enough C and enough D show up, it might actually slide backwards and produce A and B again. And then as you get enough A and B, they might react to produce C and D again, and you get this reaction that actually swings back and forth, that oscillates around. And there's one that I'll try and make it for you to show you this this idea. Who said she's gonna be late? Angel's not even gonna get in the building right now. So yes, she's let her know that there is a shelter in place, and it's probably going to be difficult for her to get inside. So there's 3 ways that we write these things. The first one is what's called a word equation, and it uses exactly what you think it does. A word equation. So was that a hand? No, was that a hand? Okay. A word equation uses words to describe what's happening in a chemical reaction. We actually use the names for things. We still use the pluses and the arrows, but something like this. I've got magnesium plus oxygen, or magnesium reacts with oxygen to produce magnesium oxide. These 2 symbols, the plus and the arrow, they shorten it a little bit, but not a lot. We're still using the full names for the magnesium and the oxygen. These are the reactants. These over here are the products. And so the word equations are there. They're not as perhaps helpful as we'd like them to be. And so to make our life even more condensed, we introduce skeleton equations. Now, skeleton equations, which is this blank here, provide the chemical symbols for the reactants and the products. You guys all have skeletons. And my daughter is very fascinated by skeletons. If you have a skeleton, what's a skeleton? It's just the bones. It's literally the minimum amount of things you need to represent a person. If I brought a skeleton in here, Mr. Clark has a skeleton. If we go into, or Mr. Lackelt actually has a skeleton. If you've taken his art class, he's got an anatomy skeleton in the pump house. You can look at that skeleton and you can see, okay, that thing is a person. If I showed you a different skeleton, you'd maybe be like, oh, that's a bird or a fish. because a skeleton is generally the minimum amount of stuff that you need to see what was once there. It's not enough to actually be a living, breathing person because you need all of the other pieces too. You need the blood and the tissue and the muscle and the fat. All of the other pieces need to be there for it to function the way it's supposed to. But a skeleton is enough for you to see what's going on. And so a skeleton equation is the same. A skeleton equation is enough for you to see what's going on, but it's not the full story. We say that a skeleton equation is unbalanced. And here's what I mean by unbalanced. In a chemical equation, if we bring back what Antoine Lavoisier said, and it says matter can't be created or destroyed, it's only moved around, you need to have the same amount of matter on the reactant side as you do on the product side. If you don't have the same amount of matter, something left or something that wasn't supposed to show up showed up, which would be weird. It would defy all the laws we understand the universe to have, and either you did something wrong or you're getting a Nobel Prize. So you probably did something wrong because that Nobel Prize would have been won already. If you take a look at this guy down here, this is an example of a skeleton equation. What about this equation breaks the law of conservation of mass? Take a look at what's there. Yeah, Lamise. Where? And why is that a problem? You don't necessarily have to have the same amount of oxygen as magnesium, but you need to have the same amount of oxygen where else? In Paris, your hand was first. Yeah, this is the oxygen is the problem. Here you've got two oxygens oxygen atoms, as you said, Lamise, but as Himparis has pointed out, how many oxygen atoms are there on the right-hand side? There's only one. And Antoine Lavoisier's experiment that he did hundreds of times said that if mass doesn't change between the reactants and the products, that means atoms aren't going anywhere. They have to be present at the beginning and they have to be present at the end. And so this skeleton equation, it's enough to tell us what's going on. You take the magnesium, you take the oxygen, they're going to react together, they're going to produce something new. But the skeleton equation isn't enough to show us how they're, like in what proportions they're reacting. So this right here, this is unbalanced, which is a problem. It breaks the law of conservation of mass. And so, flip the page when you're ready. We're going to go out of our way to balance chemical equations. You want to create a balanced chemical equation because according to the law of conservation of mass, atoms cannot be created or destroyed in a chemical reaction, just rearranged or moved around. So in a balanced chemical reaction, the same number of atoms of each element must be present on both sides of the arrow. So before we fill in that next bullet point, take a look at this equation here. This is the exact same equation I gave you on the previous page, but it's got some extra bonus information here. And in a full-blown balanced equation, this is what that bonus information is going to look like. I've still got Mg, I've got O2, and I've got MgO on the right-hand side. But what else do we have there now? Malik's saying I have twos. Where's our twos? Which twos are you referring to? That guy there. And the 2 in front of the MgO. In math, you guys, in whether you're taking math, well, you've all taken Math 9. In Math 9, when you were looking at linear equations or polynomials, you had numbers out front attached to variables to represent how many of that variable was present. These numbers have a name in math. What do you call them? Starts with a C. A coefficient. These guys right there, and it's actually on the page there for you. The number placed in front of a chemical formula is called a coefficient. That's this guy here and this guy here. And in science, in a balanced equation, in chemistry, they do the exact same thing that they do in math. They tell you how many you have of the thing that's immediately next to it. So if you have, in math, if I said the equation was like 2x equals 6, that means you have two x's, and together they equal 6. So then each x is worth what? 3. If 2x equals 6, then x equals 3. It's the same idea here. By putting a 2 out front here, that means I have 2 atoms of magnesium. I'm adding, and by putting the 2 out front, it means that those atoms are separate. They're not attached together. So I've got 2 atoms of magnesium. I'll write that down here. 2 atoms of magnesium, right there. And those guys are unattached. This O2 here also means I have 2 atoms of oxygen. But why are they written differently? Oh.
Attention all staff and students. The shelter in place is all clear. The shelter in place is all clear. The shelter in place is now canceled. Please resume your regular activities. Thank you.
Answer my question and then we will go to the lab. Why are these two 2's written differently? No. One is a gas, one is a solid, but that's not the full reason why. The oxygens are bonded together. What kind of bond? A shared one. The shared bond is called a covalent bond. Magnesiums are all positive as an ion. So if you have pure magnesium, they cannot be, they're not ionically bonded together because all of them want to just give up electrons. The whole point of the stuff that we've done already. They're just, as atoms, they're neutrally charged, they're clumps together, they're just hanging out. There is no bond between them. These guys, though, the oxygens, if you recall, oxygen has space for electrons. It wants to bring more electrons in. So when you clump a bunch of oxygens together, they react together, they clump down, and they create molecules. Covalently bonded things are called molecules. This we call a diatomic molecule. These oxygens are going to be bonded together. So I've got 2 atoms of magnesiums, not bonded, they're unattached. I've got 2 atoms of oxygen, they're bonded together. And now I've got this thing, this 2MgO. That 2 out front, and the MgO over here. What's going on there? Why is this thing listed as MgO? Sorry? You say because it is? But why? When I've got MgO, I mean, you've been looking at this stuff already. I made you draw Lewis and Bohr diagrams of this thing. What's MgO? Sorry? It's magnesium oxide, and both of you said it at the exact same time. This is magnesium oxide. The magnesium and the oxygen are bonded together. How? It's an ionic bond. Because magnesium wants to give up electrons, oxygen wants to take electrons, and so you get this structure. They're built here. Now, depending on how magnesium and oxygen come together, we may or may not have subscripts down here. But if we look at the charges for magnesium and oxygen, magnesium's +2, oxygen's -2. So you just need one of each. Yes, Michael, could you open the door for Angel? Actually, you could just leave the door open, not to. Oh, she got into the middle door. Nice. Welcome here. Leave the door open. Leave it open. So you got 2 atoms of magnesium unattached, two atoms of oxygen covalently bonded. When you mix these two, the covalent bond with the oxygen breaks, and you form an ionic bond between the magnesium and the oxygen to make this magnesium oxide. And then the 2 out front here means that you now have this guy here. So I'm running out of space. I'll use a different color, and I'll point this arrow over here. What this 2 means is you now have 2, what's the word I want to use there? You have 2 separate magnesium oxides. Say it that way. They're not molecules. We can't use that word there. Because a molecule represents a covalent bond. But now you've got 2 separate magnesium oxides. You've got MgO and you've got an MgO. So the coefficients out front represent how many you have of a particular thing. The subscripts down here also tell you how many you have, but these ones are bonded together, these ones are not. Okay, we're going to pause it there, and we're going to come back to balancing equations tomorrow, assuming we get the lab. Now, what we're going to do now is we're going to head to the lab. Lexi, was that a hand? Is that a hand?
No.
No, okay, cool. Leave your stuff, except for the handouts that I gave you. You will need a writing utensil. You will need a phone to function as a stopwatch. But otherwise, we are going to head to the lab. Here we go. Angel is the only one that can get one of these. Got one of these on your way by. There's 2 on the corner there. I need my denture cleaner. Go to the lab. Angel, here you go. You guys are going to work in 2s or 3s. Need a writing utensil each of you. Okay. So we'll finish that tomorrow. We'll likely be in the classroom for that one, but the lab is open. We'll finish that tomorrow. When the bell goes, you may also go. Have a good day. It was a great class. But we did it. If this belongs to any of you, I don't know if I asked you guys about this yesterday. Does this belong to any of you?
I just take it.
Give me another day, and then we can auction it off. Wrap it. You can wrap it. No one claims you want to wrap it off. Not auction. Wrap it. Everyone who's interested puts their name in a hat. We pull a name. Okay, when the bell goes, you may also go have a good day.
I see somehow has the best outfits, but sometimes has some interesting. This is
Okay, see you guys later.